So return our discussion back to sorting. We've already covered two kinds of sorting algorithms. No, three already. Right? We've covered quick sort, merge sort, and insertion sort. So we use insertion sort just to get a timing equation out of it. Now what we'll do is take a look at, suppose we had, and so in all the sorting examples we've had, the numbers we're sorting could be anywhere from negative infinity to positive infinity. But suppose we had the knowledge that all the numbers are between 1 and 10,000, like just some constant, and it could be a pretty big constant. So let's say all the numbers we're sorting we know are between 1 and 10,000. Could we use that to our advantage? So this is an algorithm called the counting sort, which basically says, well, if we know that everything we're sorting is an integer between 1 and 10,000, or 0 and 10,000, why don't we just create an array of size 10,000? Initialize all the counts to 0, and then run through all the input, and every time if we see a 16, we add 1 to the 16th element of the array. You know, count equals count plus 1. And just count up how many times we see everything. So then we'll have an array that looks something like, you know, element 0 has a count of 2. That means we've seen 2 zeros. If element 1 has a count of 0, that means we didn't see any 1s. If element 2 has a count of 4, that means we saw 4 2s along the way. So what we could do is just go through all the numbers. Every time we see a number, we add 1 to the count. So that's going to be n operations. And then at the beginning, we have to initialize all the counts to 0. So basically, we go through the whole array, initialize all the counts to 0. Then we go through the whole array, we read the integer and add 1 to it. So the first step is going to take 10,000 steps. Whatever the question gave us as, you know, I promise you all the numbers are between 1 and 10,000. So it'll take 10,000 steps to initialize that to 0. Then go through the array, count them all up, and then once we have all the counts, go through another array and print them out each time we see one. So if we see 4 2s, we would say 2 2 2 2 in the answer, because we're seeing it 4 times. So what's the running time of this algorithm? Well, it's whatever that first number they give us, like 10,000, plus n. There's n steps plus 10,000 steps. And that's could be better than n log n if n got really large, because log base 2 of n could get to the point where it's much larger than 10,000 if n got, you know, ridiculously large. So we could use an advantage. If they told us for the question we have a fixed number, a fixed range of the numbers to be in, we just create an array with that range. So that's called a counting sort. Similar idea is a bucket sort. This is where we do not have knowledge of a range of the numbers, but what we can do is we can just divide the number of elements in the array by some factor and create a bunch of buckets. And then what we can do is we ask ourselves, what bucket does it go in? What bucket does the number go in? And add that on to maybe the end of a linked list. Each of the buckets has its own linked list. So we have like B buckets in this case. We take the number and divide it by the range of the numbers. So this would be, again, if we knew a range of which the numbers can be in, rather than have an array like the accounting sort, we would have just buckets. We divide them up into some finite set of buckets, throw them onto an end of a linked list, and then we have, at the end of our sort, at the end of throwing everything into a bucket, we have B, a bunch of arrays, B sub I, and we do like maybe an insertion sort. Hopefully they're small enough that the sorting wouldn't matter as much. And then we take all those sorted linked lists and link them together. So does that make sense? Like, so for example, if the numbers would, let's say once again the numbers were between 1 and 10,000, we could throw them into buckets for the first 1,000, the second 1,000, the third 1,000, the fourth 1,000. Then sort those buckets and then link them all together. So we'd have n steps, we'd have to go through all n numbers to figure out what linked list to attach them onto the end of. Then we'd have, let's say in that case, we'd have 10 buckets. We'd have to run 10 insertion sorts, and then link those results all together. Okay, so the best case scenario is the linked lists are all of length 0 or 1. That would mean we had a lot of buckets. There was like one bucket for every number that was in the list. The worst case scenario is if everything got mapped into one linked list, which really means like nothing's been done. We ran through all the numbers and then just made one big linked list out of them. Now we have to sort the linked list. It's almost like we're starting the question over again. And then the average case would be where there'd be a little probability theory involved, but it would be what's the average size of the intermediate linked list, and if they were small enough, if we had, the right choice of buckets compared to input numbers, we could argue that the sort would be small enough. Let's say, for example, all the linked lists are on average have 6 elements to them. Well, a sort of 6 elements would take actually constant time. It would be like 6 squared, which is 36, which is a constant. So you could make an argument if you had the right size of buckets and the right size of numbers, you could argue that this could be a linear time sorting algorithm. But again, this algorithm requires that we know information about the numbers before we start. So just like the counting sort, we'd have to know some kind of information, like a range on them. Another type of sorting is what's called a radix sort. So this is an example where we do a finite set of bucketing. So it's really like the bucket sort, but an extension of it. So for example, suppose we knew all the numbers were between 0 and 999. What we could do is we could take the original batch of numbers and then sort them so all the 100s are grouped together, all the 200s are grouped together, all the 300s, 400s, and so on. In this example, we have just 1s, 2s, and 9s. Then go into each of those sublists, or those sub-buckets, and sort these. We sort them by their second digit. So these are both 2, so they didn't get changed. The 2 4s got grouped together, and the 2 5 was put down here. And then the 960 got put to the top, and 977 and 971. They're being sorted based on their second digit. And then on the third phase, we go through and we sort by the first digit within the groups of the previous. Each layer gets smaller sets of groups that we're sorting into. So again, we're taking advantage of the fact that we know all the numbers are between 0 and 999. If that didn't work, if all the numbers were up to 9,999, then we'd have a fourth, what they call a radix. In this case, the radix is 10. Yeah.
The only question I have is, we're showing in each, we're talking about buckets, and we sorted.
Well, maybe I should.
Buckets on, sorted on the tens place.
I shouldn't use buckets because that confuses with bucket sort, but.
Right, but yeah, I mean, I'm not really keeping each of those like I would keep a bucket, am I?
Right, we're
I'm just
basically,
with
after the first pass, all of the ones that start with the same highest order digit are grouped together. Then within that group, we go by the next digit. And we just sort based on the next digit.
When I get to the next, when I've sorted on tens, do I still, I've gotten rid of the bucket with the hundreds sort, right? I mean, the idea of buckets seems permanent to me.
Well, no, see what we're
Unless I'm
doing,
missing
what we're doing here is, after the first pass, right, these are all random numbers.
Right.
Now, all the ones that start with 100 got grouped together. Now we're going to sort, and it's going to be exactly like bucket sort. That's why this came right after bucket sort. We're going to sort these numbers into 10 buckets, 0 through 9. Now these two numbers got sorted into the same bucket, so there was really no progress on the second pass. When we did 127 and 126, they were put into a separate bucket, the ones that start with 100. Then they got sorted based on their second digit, which accomplished nothing. So really what happened here, we put 127 in a linked list, 126 in a linked list, and didn't bother to sort those linked lists because they were in the 2 bucket, the second digit of 2. So maybe like in this example, we made, out of the 9s, the ones that start with 9, we sorted them into the linked list that starts with 6 as the middle digit, and then these 2 got put into the linked list that starts with 7. And then those 2 linked lists, this linked list and then the one with these 2 links on it, got merged together into one linked list. So it came out looking like this. 960, 977, and 971. And then we just do the same thing on the next radix. They call it radix. So in this case, we use divide by 10 to be the radix. We could have done divide by 2 and so on. So it's a repeated implementation of the bucket sort, but whatever you pick as the radix is going to decide what bucket it goes in. So here's an example of the code, and this is where like computers use ones and zeros. So if we used a radix of base 2 instead of like the last example of base 10, we could just take the high order bit, all the ones that start with a 0 go into one bucket, all the ones that could start with a 1 go into the next bucket, then divide those into buckets based on the next bit. And the running time of the algorithm would be, it'd end up being n numbers times log base 2 of whatever the maximum value the computer could hold in bits. So that's really n times the number of bits that the computer can hold, because each pass is one of the bits. Okay, so now a slightly different topic, but this is going to come up where we could actually, when we're doing our accounting of what the running time of an algorithm is, suppose we had a piece of code that looked like this. For I equals 1 to n, call some procedure. And if I told you that that procedure has a running time of, linear, what would you think the overall running time of this algorithm is? So intuition says, well, I'm going to do something n times, and each one of these runs takes proportional to n steps. That looks like n times n would be n squared, right? Right, intuition would tell you, this little 2-line algorithm, I equals 1 to n, call a subroutine, and this subroutine on average takes n steps. Then on average, the overall algorithm would be n squared. But suppose each call to this routine was kind of linked to previous calls. So suppose it said something like, while the index is, like let's say for example, each time you call the routine, it went so many steps through n and then stopped there. And the next time it got called, it picked up where it left off last time. Now technically that algorithm, because you don't have control over how far through the array it goes, you'd have to argue it's on average linear time. It could go through the whole array, it could go through half of it, it could take 1 step, it could take no steps. But you'd have to argue it's a linear time algorithm, because you don't know how far it'll go. It's the same argument if we go searching through a linked list for something. We might get lucky and find it on the first link. We might get real lucky and have to wait till we hit the end. But we say that the search is linear time, because on average maybe it'll go through half the array and we'll find it. So it's a linear time algorithm, even though sometimes we might get it at the beginning, we might get it at the end. But if there's some property about the p function that says if you call it n times, the total amount of work of all n calls is only n, not n squared each time, then the last question, instead of doing the accounting for what the running time is, this is basically saying, if we call this procedure n times, and this procedure runs on average n proportional to n times, it looks like n squared. But if we can argue that all n calls added up only takes n times, because we look further into what that procedure does, then we could really argue both of those lines of code only take order n. So we're taking the overall, we're amortizing, like breaking it down on a per cost basis, and per call on average over a series of calls, and saying the whole thing together is only order n. So that's just a kind of an accounting thing we want to keep in mind, because it'll come up shortly. Okay, so now, we talked about heaps in a previous class, and now we're going to say, can we use heaps to sort something? And here, like the general idea of using a heap to sort something would go like this. If we decided that we wanted to create a heap, if we decided that we had a heap, let's say we had a group of numbers and we built a min heap out of them. So let's say we had a min heap like this. Okay, that's a min heap. Oh wait, I gotta do one. Put a 55 here. Oh wait, what am I doing? Uh, 4477. Okay, that's a min heap. The root is the smallest, every child is bigger than the parent. And that's true in every case, right?
Yeah.
Okay. Suppose we wanted to, if you already had a heap for some reason, someone gives you a heap, right? People are always walking up to you giving you a heap, right? So if someone gave you a heap and you wanted to print everything out in sorted order, what can you do? Pop the heap, and obviously the root is the lowest, so that goes into the first slot. Now, can we turn this heap, which now has a missing spot at the root, can we turn this back into a heap?
Check for the.
So really, what we want to do is we want to pop the root, turn it back into a heap, pop the next one, turn it back into a heap until we're done. And then we'll have the array sorted. How can we turn this back into a heap?
Just keep checking the children for the smallest one and then make the smallest one in the new root.
Yep, so this guy comes up to here, now we got a problem here.
Do the same thing.
Do the same thing, check the two children, always promote the smaller one, and we have a problem here, but we don't care, it's the root now. Now we have another heap again, and then pop. 22, and now this guy's gone, and we do it again. Oh, I wrote 32, what was that, 22?
33 shouldn't be.
Was it 33?
Yeah.
Okay. Okay, the smaller comes up here, 33. This guy's now the problem, 66 comes up to here, and we have a min heap again. And just keep doing that till we're done. So now the question is, how do we get a bunch of numbers to become a heap in the first place? So it looks like this algorithm is create a heap, and then repeatedly pop the smallest one and then return it into a heap again. So how do we make something originally a heap? So there's a routine in this code called heapify. But if we had a group of numbers that were random, if they were a random set of numbers, so these are just random numbers, and then we said, let's turn this thing into a heap. What we could do is, for every number, we could, well, first of all, to represent a heap, we could use that trick. We can have an array, and basically, this is number 1, 22, this is number 2, number 3. So basically, here's the root, and here's one child, and here's the other child. Then this one's first child is here, and the one right after it. 77, 55, 66, 33. And this one's 2 children on this one and this one. So we could kind of mathematically in our head just keep track of who the children are, right? We don't have to even create the nodes and say left child, right child. We could actually have an array and just know the first one's 2 children are the second and the third. The second one's 2 children are the fourth and the fifth, and the third one's 2 children are the sixth and the seventh. And that could go on and on forever. So if we want to take a series of random numbers, which is basically an array that are random, and turn it into a heap, what could we do? We could pick the last number and put it up into the top and then heapify that into its right spot. And in this case, it would go, it could go in either direction. If we heapified it into everything, not counting this spot, then we would say 33 is bigger than 22, so it should become a child of it, and then we could go to either side. Or we would go down to this side, and 33 would end up coming here. Then we would take 66 and put that in its correct spot. So by putting a 66 into the top, 66 would come, again, back down to this spot. Let's say, for example, this one. This one would go up to the top, and 11 would want to stay on top, and the 22 would get pushed down. So for each element in the heap, we would call this routine where we heapify it by putting it into the top and then finding its correct spot. And if we did that for each element, by the time we were done, we'd have a heap. So that's what these routines are. So this is really just coming up with a new data structure, but this data structure has some interesting side effects. So we have a heapify routine, which takes an array and an index.
You didn't turn the camera.
Oh, good. Thanks. So, yeah, heapify, the heapify routine takes an array A and an index, and it traverses down the tree, the binary heap, and inserts the passed in index to its current spot. The build heap is a routine that will repeatedly call heapify on each element until we finally have a fully built heap. And then, so those will be the build heap will call the routine heapify over and over and over for each element. Then we'll eventually have an initial heap. And then heap sort is going to do what we said. It would just pop out the lowest element and then re-heapify the heap, so it becomes a heap again, and do that again. So here's pseudocode for the heapify routine, and then the build heap routine, which just repeatedly calls the heapify routine. And it turns out technically we only have to call it for half as many elements, because one of the side effects will be the bottom set of children will be automatically heapified. And then the heap sort algorithm says, step 1, take your random collection of numbers, build a heap. So step 1 is building a heap. Now right away, how long does, this is our sorting algorithm, it's the heap sort. How long does it take to build a heap? Well, for every element, we have to call a routine that keeps comparing itself to the children and walks down the tree. So the walk down the tree is log n times. And we have to do that for each element. So this step right here runs n log n times. Then what we have to do is, the next step is to pop the smallest one into the first spot, then call reheapify, which walks down the tree, which also takes log n steps. So the first step takes n log n time, and then the second step, now that we have a heap, to build a sorted list from it, takes another n log n time. So the overall algorithm is going to be n log n plus another n log n, which is 2 n log n, but that's n log n. That makes sense? If you have 2 steps that take the same amount of time, when n gets unusually large, it still grows at a rate of n log n to the original algorithm. There is one side effect that this structure has. If you ever,
You said n log n plus n log n? is what you said.
Yeah, so, yeah, basically what
I
I'm
just
saying
wanted to
is,
make sure.
yeah, what I'm basically saying is, any algorithm, let's say you have an algorithm that has 5 steps to it, and one step is n squared, another one is n log n, another one is whatever. The running time of your algorithm, the order, the big O notation, is gonna be whichever term is the largest of them all. Because when n gets ridiculously large, that's gonna be the dominating step. So, if we had one step that was n log n and another step that was just n, we would say the overall algorithm is n log n, because that's the dominating one. This has 2 steps to it, and both steps happen to be n log n, so they tie each other. So it looks like there's extra overhead compared to the other n log n algorithms. You might wonder, why would we want this? But one of the side effects of maintaining a heap is, at any point in time, if we wanted to know what's the smallest element, it's the top of the heap. In a min heap, it would be the top of the heap. So if we found ourselves needing a way of sorting things, but also from time to time we want to know what's the smallest one, this would be a good structure to keep. Quicksort wouldn't do that, and merge sort wouldn't do that. So that happens to be one side effect of this.
So with heap, we really don't care what the makeup of the elements are. We just want max and min.
Right.
We don't really care what's the child of blah blah.
Right. Yeah, and we don't care if I guess what would it be, the cousins? If cousins are much bigger than other cousins? Because all we care about is that, all we care about with a heap is that we keep the property that the parent is bigger than or smaller than, depending on if it's a min heap or max, than the children.
How do we deal with ties?
You could create the heap so that the children can be tied with their parents. So, for example, a min heap could be like this. 55. So this would be okay.
Okay, so say that the top element now is 55, but prior to that, 44s and 77, or you couldn't do that. What I'm saying is, how do we deal with promotion if we pop off the top and there's a tie at the next 2 elements?
This is a min heap, right?
Yeah.
Okay, that's okay. So yeah, the point I want to get across was, it's okay that,
You don't have duplicates.
oh, right, we wanted to duplicate. This is still a min heap, right? And it's okay if the child ties a parent. This is a min heap. And it's okay that this is smaller than this, even though this one's closer. Like, you would think the closer you are to the top, the smaller you are. That's not really true. This is smaller than this, but that's okay.
So what my question, I guess, is prior to that, say 25 was min and 33 was where 77 is now promoted to.
Oh, okay, you mean to tie at the same level?
Right.
Okay.
What's the criteria? How does that break down?
And if this was...
Just something lower.
So
we pop
so
that
this
off
is
and
still
now
a,
we need
this
to
is
bring
still a
up-
min heap.
Right, so now we pop off 22 and we need to promote.
Right, so normally what we do is say which is smaller of the children.
Right.
If it's a tie, I guess you could pick either one.
So it's just arbitrary.
Yeah.
Okay.
And then, yeah, if we pick this one, then we have to say which one out of these. So, have you ever heard, now that we've talked about stacks and heaps, have you ever heard when you when you're programming in, well, in C++, this would have come up, but no, this is true in Java too. In Java, they say when you make a primitive type, int x, you declare a variable called x. You get a piece of storage called x. If you created a class called, let's say, a person, and you say person, p, now you have to say equals new person, right? And you call the constructor, and it creates a piece of storage for you, right? Have you ever heard the expression where they'll say, this storage goes on the stack, and this storage goes on the heap?
Yeah.
Have you ever heard or read that in the book? Okay, so we've talked about stacks and heaps now. Do you know what, did they ever explain what the stack or the heap?
I mean, I got the explanation like 2 years ago or something like that.
Okay, but now that we've talked about stacks and heaps, a stack is something where things are organized, layered on top of each other, and you can only see the top. And when you're done with something, the top part gets deleted away. A heap is like a big disorganized pile of crap, right?
It would seem to me that the stack to determine the scope of a variable, for example. The stack
Right,
would
so
be ideal for that.
when you say, like in some Java code, if you say open paren int x, blah, 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 and then another open paren int a, and then you go close paren and then close paren. When is x and a alive? Well, in this code, x and a are both alive. When you hit this close paren, a pops off the stack, it's gone. And now only x is alive down here. So your variables are being, it's just using these data structure concepts. They're just saying, we're stacking up the variables, and as soon as I hit close parens, I start popping away the top of the stack. A heap is a big disorganized pile that kind of stays around forever. So, I don't know if heap is the greatest word to use for that, but they're just saying when you do a new of a variable, you're getting a chunk of storage, and in C and C++, you actually have the responsibility of deleting it. But in Java, they came up with this concept of if no one's referring to it, it will get deleted automatically. But the bottom line is a closed paren will not cause it to go away. Actually, your code has to say, okay, now I'm done with it, and now it goes away. So they end up calling that, they call it the heap, but it basically just means a big disorganized collection of storage that you don't just take away what's on top, you take away like a stack, but you instead take away, you take it out of the heap as needed, and you have to actually go fishing through it to find it when you go to take it away. So a programming language like C or C++, which has a lot more stack variables, cleans itself up quicker than a programming language like Java, because when you have to get rid of the storage, you have to go looking through a heap for it. But then this stuff stays around longer, so it's a more flexible language. So those are just, but you'll probably hear that. So have you read that, or is that?
Well, no, I took this class before, and the last instructor
Oh,
explained.
data structures,
Yeah,
or?
yeah.
Oh, okay, okay. But I mean, when you were taking either C++ or Java, did they ever refer to variables as heap variables and stack variables?
Some folks I read.
Okay, but that's really what it comes from. So the closed parens cause the top of the stack to get popped away, and the heap stays around until you force it to go away. Okay, so then the analysis of the heap sort is the heapify routine itself runs log n. We have to call that n times, and like I said, you don't have to call it for the bottom layer of the tree, but we have to call it for n over 2 times. So building the heap takes n log n. The calls, once the build heap is done, the swapping routines are done n over 2 times. So that has an order n, and they're called n times. So the algorithm ends up being, the overall algorithm ends up being n log n. And since the heap sort has 2 steps, each running n log n, the overall algorithm is n log n. Okay. So, and then hashing is similar to what we've talked about with the, kind of like the bucket sort concept. Hashing, sorting uses a hash table and a series of linked lists. Very similar to bucket sorting, except that you have the luxury of creating your own abstract function to decide what bucket they go in. So for example, if we wanted to have a series of numbers, a series of things to sort into buckets, we don't necessarily have to use like a radix, like what's its biggest digit or what's the first letter of the last name. We could come up with any function we want, which we're going to call a hash function. And if we put an object into the hash function, it returns as an output a bucket. So let's say, I'm using the word bucket, I shouldn't say that. It returns a hash. So let's say we decided we have, let's say we have 1,000 numbers to sort. If we decided to sort them into k equals 10 buckets, we would want to have a hash function that we throw an object, we pass an object into the function, and it spits out as an answer 1 through 10. Somehow it looks at the data and says, all right, I'm going to call this one a 2, I'm going to call this one a 5. And it tells us what bucket it goes into. And then we add it to the end of that linked list. Now this is not actually, I should really call this hashing, but if we eventually wanted to sort it, we could do that too. But hashing itself goes like this. If you want to look up one of those values now, we take the value we want to look up, run that through the hash function, and it'll tell us which linked list to go looking on. And then we would go just look on that linked list. Now the thing is this, if we had 10,000 numbers and only had 10 lists, on average, how big would these lists be once we hashed them all? So like I say, hashing is, you call the function, the hash function, passing in the object, it tells you which linked list to put them on, and then we attach it to the end of the linked list. We could decide we want to sort the linked list or not, that's our call later on. But if we hash the object, put it on the linked list, now if we wanted to go look one up, we would hash the thing we're looking up, tells us which linked list to go searching, and then we'd search that one. So it could cut down work for us. But if we had, let's say the ratio of the number of numbers, our n, compared to the size of k, suppose k was dramatically smaller than n. For example, suppose we had 10,000 numbers and k was 10. What would we expect on average, how big would one of the linked lists be?
100,000.
Half of 1,000.
Wait. If we had,
You said 10,000, right?
well, let's say we had 10,000 numbers and k was 10, there's 10 linked lists.
So I'm dividing 1,000 by k.
10.
10 in this case.
Well, I'm sorry, you're dividing 10, did I say 10,000 or 1,000?
10,000. you said.
10,000, okay. Divided by, so each linked list would be on average 1,000 long.
1,000. And
Right.
on average, I'm figuring half, 500. I don't know how long. Oh, I'm gonna have them all.
Yeah, in other words, so step one, we're gonna take all our items and then hash them
Right.
into this hash structure. And then if we went searching for one of the items,
I go directly to
to the
one of
linked
100.
list
I mean,
for that.
1,000.
Right, so each one on average would be 1,000. Some might be bigger, some might be less, but each one would be on average 1,000. But at least now, how long does it take to search this structure compared to if we had it all on one big linked list? If we had it all on one big linked list, it would be order n. Doing it this way, it would be,
10th of the time.
And divided by 10.
on average, 1/10 of n, but then there's also the time this new hash function, how long does that take? Now, if you made it real complicated, where it takes like the person's first name and their age and divides it by, if it got some real complicated thing, it's gonna take up that much amount of time. So you don't want the hash function to be too time consuming. But we have to run the hash function, and then that takes us to a much shorter list than before. Now, if we did it like this, so now, just to make this effective, what would be a good ratio for k to be compared to the number of inputs n that would make this work faster? So I guess really what it comes down to now, well, if k was a lot bigger than n, what would the story be?
Well, wouldn't the best case be that there's only one node in each linked list, so that
K
k
couldn't
would
be
be,
bigger.
you just multiply k times n, or multiply n by itself to make one node in each linked list, and that way you wouldn't have to search down a linked list, because the head node would be what you're looking for.
Yeah, I mean, what we would like is, well, wait, you just said something interesting. You said k could never be bigger than n?
Well, what I said, yeah, it seemed to me that k, in other words, you're gonna divide k, I mean, you're gonna divide n by k.
Yeah, so
Well, you never
we
want it
have,
to
we
be more
have,
than one, the result would never be more than one, which is the one bucket or whatever, I think that gentleman was talking about, right?
the result.
So missing something.
Well, we have the freedom, as long as we have enough storage. This is basically gonna be an array of references to the head of a linked list. So this is, like, if these were nodes, let's say we had some class called node.
And if there was only one item, finally, in each of the linked lists, there's a linked list of one item.
Right, that's what he's saying, the
Which
best
is what he was
case.
saying, and then I was saying, well, then k equals n gives you one. I have n things.
Okay, so what you're
You see
saying,
what I'm getting?
if we chose, all right, so let's say we have one extreme where k is a lot smaller than n. That ends up being, it's probably still good to hash things. So we're putting things into a structure because we want to do a lot of lookup. So it ends up being, hashing is one of the most popular ways to store stuff if you're going to be looking up things a lot. If k was a lot smaller than n, then the good news is our linked list would be smaller, but they still could be pretty big. But at least we're not searching, our searching time would be running the hash function and then going through a linked list that's maybe 1/10 the size of the original linked list, which is still an improvement, assuming your hash function is quick. But if now let's go, we'll call this the middle extreme, where k equals n. Could we say that on average the linked list will be of size 1? Actually, it now becomes a probability question, because a lot of times the hash function will put elements on the same list. So maybe half the list would be empty and half the list might on average be size 2. A few of them might be long, like 10 or whatever, but that would still be good. And then what if we went the other extreme and made k a lot larger than n? Now this involves some knowledge that we know what n is before the thing starts, because we have to decide k before we even write the program. But if we had that knowledge and we made k a lot larger, let's say we had 1,000 numbers, but k was 10,000. So we're gonna have a lot of linked lists of size 0, because we have more linked lists than we have numbers. And then the ones we do have, if our hash function is good and kind of fans them out well, hopefully the linked list will be of size 1 or 2. And then this would be a really good, if we could get to the point where if we could design a hash function where we know that, and let's say k was, let's say, some statistics like k is 10 times the size of n, and our hash function is so well that the linked list is never more than 5, then it's almost like constant time looking up these things. Because looking up an array is constant time. You just say, I want to go to location 92, and you're there. And then you walk through its linked list, and if the linked list was really small, you'd find this stuff very quickly. So a hash ends up being a good structure if we're not keeping things sorted, we're just putting them into a structure where we can look things up quickly. But we'd have to come up with a hash function that says, okay, I'm looking for this particular person, and it's something that maybe takes their first name, last name, age, and produces some number between 0 and k. And hopefully the hash function is so good that if you gave it a bunch of random stuff, it would fan them out well. It doesn't keep putting them on the same list. So a good hash function is one that's quick and fans out random objects into many different buckets. And this would be the best thing for looking stuff up quickly. So I know Facebook uses, because there's so many people on Facebook, when you log in, all your friends show up on your page. And out of all the people in the world who are on Facebook, they have to look up a lot of people and say, I only care about your friends. So they'll put your login through a hash, and then it finds the linked list for your friends. That's how they get them so quickly. But that's like, hashing is the most common data structure for storing stuff, knowing that you're going to be looking the stuff up later on. And we could turn this into a sorting algorithm if we wanted to. So basically we load everything into a hash, and then whatever we determine is this, you know, how we rank things based on alphabetical, you know, whatever field we rank things on, we then go looking for, in order, though, anything with that attribute, and we look it up in the hash table and pull that one out, and then print those into a sorted list. So hashing is really not meant so much for sorting. If k is, so yeah, so the running time of a hash sort, where we first load everything into a hash, takes, loading everything into the hash takes n times the running time of your hash function. So hopefully we have a hash function that has constant time. That puts everything into the hash, then you have to go through all k lists and print them back into the original function. So the running time of this would end up being k plus n, which is worse than n. Right, let's say for example we had 10,000 numbers and we used k of 1,000,000, which is a good choice for looking up elements. But then the problem would be, the running time would be 1,000,000 plus 10,000. So if you're using this for sorting purposes, it might not be the greatest algorithm, but it's a hash is a great structure to put something in for lookups. And then I just have the best case, worst case, average case, if you want to do hash sorting. So really, right now I'm on the topic of sorting, but I'm putting in hashing, because hashing ends up being a good data structure to store things for looking up. And there's a little argument here at the end that basically says if you're doing comparison sorting, which is where we don't have any information, we don't know how many items there are, and we don't know the smallest and largest number, the minimum amount of running time would end up being n log n. And we'll revisit this towards the end of the class when we talk about complexity classes, but right now, if you have no information about what you're sorting, out of all the algorithms in the world, the best one is going to run n log n. Even though tonight we talked about some linear time ones, we had some information about the numbers, like they're only between 1 and 1,000, or there's only so many numbers, then we were able to come up with a better algorithm.